Imagine a giant cold cloud of dust and gas floating silently in the vast emptiness of space, stretching across hundreds of light years and containing the raw material for thousands of future suns. Deep inside that immense cloud, gravity begins its subtle but relentless work, pulling atoms and molecules together over millions of years. Tiny clumps slowly grow denser and harder until, at last, the temperature at the center reaches millions of degrees. Nuclear fusion ignites like a cosmic match, and a brand new star bursts into life, shining with the energy of a billion nuclear bombs every second. That brilliant star will shine steadily for billions of years, lighting up its surrounding planets and galaxies. But eventually, as nuclear fuel runs out, when that happens, the star doesn't simply fade away quietly, it transforms in spectacular fashion, sometimes swelling into a gigantic red giant that swallows its own planet, sometimes detonating in a brilliant supernova explosion so powerful it can outshine an entire galaxy for weeks. In the process, it scatters nearly forged elements, carbon, oxygen, iron, even gold, across the cosmos like cosmic seas. They the complete life cycle of stars, from their dramatic birth inside glowing stellar nurseries through their long and stable middle age, where they quietly power the universe, on the way to their dramatic death that recycle matter for the next generation. In the next 19 minutes, we are going to follow their entire journey step by step in far greater depth than ever before. We'll explore the hidden physics behind every stage, meet real stars at every phase of life, examine cutting edge telescope observations from Hubble, James Webb, and Chandra, and uncover the fascinating nuclear reactions happening deep inside stellar cores. We see exactly how stars form from the ashes of their ancestors, how they maintain perfect balance for eons, how they age and evolve in dramatically different ways depending on their birth mass, and how their deaths seed the universe with the very atoms that make up your body, the planet, and everything you've ever known. Most importantly, by the end of the deep dive, you'll understand why astronomers say, with complete scientific accuracy, that we are all made of stardust. Every single atom heavier than hydrogen in your DNA, your bones, and the air you breathed were formed inside the hearts of ancient stars billions of years ago. Stay with me for the extended journey. Grab a comfortable seat. Turn off the lights if you can, and prepare to be amazed by the greatest story in the cosmos, the life cycle of stars. That is how the universe and nature works. And today we are going deeper than ever. Let's begin at the very beginning of Earth star's life. Far from any light or warmth, stars are not born in empty space. They form inside enormous, cold clouds of gas and dust, known as multicolored clouds or stellar nurseries. The gigantic structures can span hundreds of light years across and contain enough material, mostly hydrogen and helium, with traces of heavier elements from previous stellar generations, to create thousands of stars identical to our Sun or even larger. Picture one of the dark, frigid clouds drifting through the spiral arm of a galaxy like the Milky Way. Temperatures inside hover around minus 260 degrees, and the density is incredibly low, only a few hundred molecules per cubic centimeter. That gravity never sleeps. Over millions of years, the cloud begins to fragment under its own weight, a process astronomers call gravitational instability, or the Jeans instability, named after the British physicist Sir James Jeans, who first described it mathematically. Small clumps of gas, at perhaps a few thousand times the mass of the Sun, start to collapse inward. As the material falls together, it heats up due to the conversion of gravitational potential energy into thermal energy. The same principle that makes a bicycle pump warm when you inflate a tire. The collapsing core spins faster and faster, conserving angular momentum, and a flattened protoplanetary disk begins to form around the central protostar. That disk is where planets will eventually condense. When the core temperature finally climbs to about 10 million degrees and the pressure reaches hundreds of millions of atmospheres, nuclear fusion ignites. For hydrogen nuclei begin fusing into one helium nucleus to the proton-proton chain, releasing enormous energy in the form of gamma-ray photons. At that instant, a protostar is officially born. The young star is still shrouded in its birth cocoon of gas and dust, but powerful jets of material shoot out from its balls. Bipolar outflows that can be seen with infrared telescopes like the James Webb Space Telescope. The protostar continues accelerating material from its surrounding disk, growing brighter and hotter every day. Eventually, it reaches hydrostatic equilibrium. The outward pressure from fusion exactly balances the inward crush of gravity. This is the moment a true main sequence star is born. Different molecular clouds produce stars with wildly different masses. A small, low-mass cloud might give birth to a red dwarf star that will shine steadily for 10 to 100 trillion years. Far longer than the current age of the universe, a massive cloud, on the other hand, can birth blue supergiants that exhaust their fuel in just a few million years. But no matter the final size, every single star begins its life the same way, forged from the recycled dust and gas left behind by previous generations of stars that lived and died billions of years earlier. In fact, the Orion Nebula, visible to the naked eye as a Fuji patch in Orion the Square, as one of the most active stellar nurseries in our galaxy right now, giving her a front row seat to the birth process happening live. Once a star successfully ignites hydrogen fusion in its core, it settles into the longest and most stable chapter of its entire existence, the main sequence phase. This when nearly every star, including our Sun, spends roughly 90% of its total lifetime. For a star like the Sun, that means about 10 billion years total. We're currently halfway through at 4.6 billion years old. For tiny red dwarfs, that phase can stretch into the trillions of years. For the most massive stars, it lasts only a few million years, the blink of an eye on cosmic timescales. Let's truly understand what stable means here. The star achieves perfect hydrostatic equilibrium. The tremendous outward thermal pressure and the radiation pressure generated by nuclear fusion in the core exactly counteracts the real inward-borne Earth gravity. It's like a perfectly balanced seashore of finely tuned spring, and its slight impulse is corrected almost instantly by natural feedback mechanisms. If the core gets a little hotter, fusion speeds up, pressure increases, and the star expands slightly to cool itself down. If it cools too much, gravity compresses it again, restarting the cycle. This self-regulating thermostat keeps the star remarkably constant for billions of years. The color, surface temperature, luminosity, and size of any sequence star are determined almost entirely by its initial mass, a relationship beautifully plotted on the famous Hertzsprung-Russell diagram. On the right, main sequence stars form a clear diagonal band running from the hot, luminous blue stars in the upper left to the cool, dim red dwarfs in the lower right. Our sun sits right in the middle of that band at a yellow G-type star with a surface temperature of about 5,400 degrees. Inside the core, fusion occurs through two primary pathways. For stars around the mass of the Sun or smaller, the proton-proton chain dominates. For hydrogen nuclei combine step by step through a series of reactions to form one helium nucleus, releasing energy, positrons, neutrinos, and gamma rays along the way. For more massive stars, the carbon, nitrogen, oxygen, CNO cycle takes over. In the CNO cycle, carbon, nitrogen, and oxygen act as catalysts. They have fused hydrogen into helium much faster without being consumed themselves. The reactions require core temperatures of 15 million degrees or higher, conditions so extreme that the density is 150 times that of water and the pressure is 250 billion times Earth's atmosphere. The energy produced doesn't blast straight out to the surface. Instead, it takes between 100,000 and a million years for photons to random work their way outward through the radiative and convective zones, constantly being absorbed and re-emitted by atoms. By the time the energy reaches the photosphere, the visible surface, it has cooled enough to shine as visible light and heat. The star's outer layers behave like an enormous radiator, steadily emitting radiation into space, while the core quietly continues its fusion work. During the entire main sequence phase, the star changes very little on the surface. Its size, temperature, and brightness remain almost perfectly constant. But deep inside, hydrogen is steadily being converted into helium. When the hydrogen fuel in the very center finally drops below about 10%, the core begins to contract under gravity. That contraction hits the core further, allowing helium fusion to begin in a shell surrounding the helium ash. The star has now left the main sequence and is entering O8. The transition depends critically on massive O and B type stars race through their fuel in just millions of years, while red dwarfs could theoretically keep fusing hydrogen for longer than the universe has existed. The stable main sequence period is truly the calm before the storm. It's the quiet, productive phase when the star forges the lighter elements that will later enrich the galaxy, quietly setting the stage for everything that comes next in its dramatic evolution. When the hydrogen fuel supply in the core is finally exhausted, the star can no longer generate outward pressure to resist gravity. the inner helium core begins to contrast rapidly and heat up dramatically, while the outer hydrogen burning layers respond by expanding outward by hundreds or even thousands of times their original size. The star transforms into a red giant, or in the case of the most massive stars, a red supergiant, one of the largest and most luminous objects in the universe. Let's visualize the transformation in slow motion. At the core contrast, as temperature soars to around 100 million degrees Celsius, but the surface layers pull outward so far that the same total energy output is now spread across an enormous area. The surface temperature drops to around 3,000 to 4,000 degrees Celsius, causing the star to glow with a distinctive reddish-orange halo, hence the name red giant. A star like our Sun will eventually swell until its radius reaches roughly the current orbit of Earth, swallowing Mercury, Venus, and possibly even Earth itself. Deep inside the swollen star, helium fusion now ignites through the famous triple unfold process. 3 helium 4 nuclei combine in a precise 2-step sequence to form carbon 12, releasing energy. The process is incredibly sensitive to temperature and density, which is why it only begins after the core has become extremely hard and compressed. The star develops a beautiful, layered, onion-like structure with multiple burning shells, a helium burning core surrounded by a hydrogen burning shell, and sometimes additional shells farther out. For a sun-like star, the red giant phase lasts roughly 500 million to 1 billion years. During this time, the star becomes unstable and experiences thermal pulses, periodic bursts of energy that cause the outer layers to pulsate like a giant beating heart. The pulses drive powerful stellar winds that blow off the outer envelope, a speed of tens of kilometers per second, enriching the surrounding interstellar medium with carbon, nitrogen, and other elements produced through slow neutron capture, the S process. In its final stages, the star ascends the asymptotic giant point AGB, where even more complex nucleosynthesis occurs, including the formation of molecules that will later become the building blocks of planets and life. Massive stars, though born with more than 8 times the sun's mass, experience an even more extreme red supergiant phase. The outer layers can expand to the size of Jupiter's orbit. Over 1,000 times the sun's current radius. Stars like Betelgeuse in Orion or Antares in Scorpius are perfect examples visible to the naked eye right now. Their cores continue fusing heavier and heavier elements in successive onion layers, helium to carbon and oxygen, then carbon to neon, neon to magnesium, on the way up to iron in the very center. Throughout the phase, these supergiants may lose mass rapidly through intense stellar winds and periodic eruptions, sometimes shedding an entire solar mass every 10,000 years. The red giant and supergiant phase is not merely the beginning of the end, it's one of the most important recycling stages in the cosmos. The star is actively returning the elements it has spent billions of years creating back into the interstellar medium through powerful winds and mass loss. The enriched clouds will later collapse to form new stars and planets. The red giant phase is dramatic, beautiful, visually stunning when observed with telescopes, and absolutely essential for the chemical evolution of galaxies. Without it, the universe would still be made almost entirely of hydrogen and helium. For stars with initial masses similar to our Sun or up to about 8 solar masses, the final act is relatively gentle compared to their more massive cousins, that's still spectacular in its own way. After the red giant phase, the outer envelope becomes so loosely bound that term pulses and stellar winds eject it entirely into space. The ejected material expands outward, forming a glowing planetary nebula, one of the most beautiful objects in the night sky, with intricate shells, rings, and filaments of gas illuminated from within by the hot, exposed core. What remains behind is a wide, draft, an Earth-sized remnant that packs up to 1.4 times the mass of the Sun into a sphere roughly the diameter of our planet. The mass limit is called the Chandrasekhar limit after the Nobel Prize winning astrophysicist Subrahmanyan Chandrasekhar, who calculated it. The white dwarf is supported against further collapse, not by fusion, but by electron degeneracy. Pressure, a quantum mechanical effect where electrons are packed so tightly they cannot occupy the same quantum state. The density is astonishing. A teaspoon of white dark material would weigh about as much as an elephant on Earth. No fusion occurs anymore. The white dwarf simply radiates away as residual heat over trillions of years, slowly cooling from white hot to red, then infrared, and eventually becoming a cold, dark black dwarf. During the planetary nebular state, which can last for 10,000 to 50,000 years. The star sheds its outer layers in multiple bunches, releasing vast quantities of carbon, oxygen, nitrogen, and other elements that were created during its red giant phase. The elements mix thoroughly with the surrounding interstellar medium, becoming raw building blocks for future generations of stars, planets, and even life. Planetary nebulae often display practically complex and symmetrical shapes. Our galaxy rings butterflies shaped by the interaction of stellar winds, magnetic fields, and sometimes the presence of a binary companion star. Famous examples include the ring nebula M57 and Lyra, and the helix nebula in Aquarius, both easily photographed with amateur telescopes. Even in that, low and medium matched stars play a vital role in cosmic recycling. They quickly return their manufactured elements to the galaxy without the violence of a supernova, ensuring that the next generation of solar system will be chemically richer than the one before. In that peaceful way, they complete their life cycle and contribute to the ongoing chemical enrichment of the universe. For stars born with more than about 8 times the mass of the Sun, that is nothing short of cataclysmic. When nuclear fusion in the core finally reaches in iron 56, the process comes to a sudden, irreversible halt. Iron is the most stable nucleus in the universe. Fusing it into heavier elements no longer releases energy. It actually consumes energy. At that precise moment, the star loses its primary source of outward pressure and can no longer fight against its own crushing gravity. The iron core collapses in less than 1 second, shrinking from roughly the size of Earth down to a sphere only about 20 kilometers across, smaller than a typical city. The density skyrockets to levels higher than the nucleus of an atom itself, and temperatures reach 100 billion degrees Celsius. The catastrophic collapse releases an unimaginable flood of neutrinos, nearly massless particles that stream outward at nearly the speed of light, carrying away 99% of supernova's energy in a matter of seconds. The outer layers of the star, still falling inward, slam into the now richest neutron core and repelled violently, creating an incredibly powerful shock wave that races outward. This explosion is what we observe as a Type II supernova, or Thai LBLC in some cases. For a few brief weeks, the dying star can shine with the brightness of an entire galaxy containing hundreds of billions of stars. The plasma wave exacts on the heavy elements forced throughout the star's life, and many new ones created in the extreme conditions of the explosion into space at speeds exceeding 10,000 kilometers per second. Depending on the exact mass of the collapsed core, the remnant left behind is either a neutron star, a black hole. If the core mass is between roughly 1.4 and 3 solar masses, it becomes a neutron star, an object the size of a city, but with a mass of the sun, spinning up to hundreds of times per second, and often appearing as a pulsar that emits regular beams of radiation like a cosmic lighthouse. If the core is heavier than about 3 solar masses, gravity overwhelms even neutron degeneracy pressure, and the remnant collapses into a black hole, a region of space-time where gravity is so intense that not even light can escape. Even after the initial explosion phase, the expanding supernova remnant continues to glow brightly for thousands of years. It lights up nearby gas clouds, compresses them to trigger the formation of brand new stars, and spreads the newly synthesized heavy elements far and wide. Famous historical supernovae include the Great Nebulae from the supernova observed in 1054 1054 AD and SN 1987 A in the large Magellanic Cloud, whose remnant we continue to study today with modern telescopes. The violent deaths are the universe's most efficient factories for creating and distributing the elements essential for life and planets. Every single element heavier than helium that exists in the universe today was forced inside stars or during their explosive deaths. A process known as stellar nucleosynthesis, hydrogen and most of the helium we see were created in the first few minutes after the Big Bang, when the entire cosmos was hot and dense enough for primordial fusion. But everything else, the carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, even the gold in jewelry, were manufactured deep inside stellar cores or in the extreme conditions of supernova. Low and medium mass stars like our Sun are responsible for producing carbon and oxygen during the red giant and IgB phases when they burn helium via the triple alpha process and subsequent reactions. These stars also contribute nitrogen and some heavier elements through slow neutron capture, the S process, which occurs over thousands of years in the stellar interior. Massive stars go much further. In their final stages of life, they fuse elements on the way up to iron in their unlayered cores, each shell burning a different fuel at higher and higher temperatures. When the massive stars explode as supernovae, the incredible heat, pressure, and neutron flux enable rapid neutron capture, the R process, creating elements heavier than iron, including gold, platinum, uranium, and many rare earth elements. The supernova plus itself synthesized additional nuclei through explosive nucleosynthesis. Incredibly, a single supernova can produce enough gold to fuel several Olympic-sized swimming pools. When stars die, whether centrally through planetary nebulae or valley to supernova, they do not simply vanish. They return on the newly created elements back into the interstellar medium. Gravity then gathers the chemically enriched gas and dust into new molecular clouds, which one day collapse and give birth to the next generation of stars and planets. They are the grand cosmic recycling loop. Each successive generation of stars is born from material that is progressively richer in heavy elements, which is why our sun is a population one star containing about 2% matters by mass, while the very first stars in the universe were almost pure hydrogen and helium. In a very real, scientifically precise sense, we truly are made of stardust. Every atom in your body, except hydrogen, was forced inside ancient stars billions of years ago. The calcium in your bones were cooked in the core of a red giant. The iron in your blood came from a supernova explosion. The oxygen you breathe was exhaled by dying stars long before our solar system even existed. Stars are not just beautiful points displayed in the night sky. They are the cosmic factories that build the universe we live in and the very chemistry of light itself.